we discussed the physical aspects of a PN junction. Now let's try to understand the electrical behavior of a PN junction. So we saw that a PN junction is consisting of P-type region and an N-type region, so PN junction. Now, what happens? A P-type region has excess of holes, so the hole density is basically Na, and electron density in the equilibrium N0 is going to be Ni squared divided by Na. Similarly, for donors, the electron density is going to be Nd, and P0 is going to be Ni squared by Nd, right? So let's assume that we have doping concentrations in the range of 10 power 15 or so. Let's say Na is equal to 10 power 15 and D equal to 10 power 16, just for example. Okay, this is typical ranges. What would happen? What do you expect? So the P region has excess of holes, while the N region has excess of electrons. And whenever you have this concentration gradients, we have seen that there is this exchange, there is a diffusion that happens. So basically, holes will diffuse in this way. Holes will diffuse into the N side, and electrons will diffuse into P side. Right? So when will this process stop? Will it go on forever? That's something to think about. Okay. So what happens when holes diffuse into the N side? Holes are essentially positively charged particles. So when they go, what you're left with is an acceptor ion, which is having a net charge of minus, right? So whenever your holes move into the N side, you leave behind an acceptor charge, so which I'll represent by a negative sign here. All right. So it leaves some negative charges whenever this transfer happens, and correspondingly, there's going to be some positive charges which are left behind because of the donor atoms. So wherever there's a donor atom, electron is going to get away from that. So the resultant charge would be negative, positive. Okay, and remember, these are fixed charges. Okay, these are fixed charge, and sometimes we call them as space charge. Okay, to distinguish it from the free charges. Electrons and holes are the free charges. They can keep moving around in the lattice, whereas the fixed charge or space charge cannot move around in the lattice. And also another aspect to think about it is, since we have removed electrons and holes from here, so this region, right, in the blue, free charges are removed, right? Hence, we also call it the depletion region. So the free charges are depleted. Depletion means reduced. So since in this case, actually, you don't have any free charges, so you have a depletion region without free charges. Whereas, if you look at this region, we call this as a quasi-neutral region. And this also is called as quasi-neutral region. Okay. So essentially, these are neutral regions because they have equal number of acceptor and holes and donors and electrons. So these are not ionized. Okay, these are not ionized. Oh, sorry, I should not say that, because when I say ionized, you might confuse with the donor ionization. So donor atoms are ionized, but you have equivalently holes and the acceptor ions equal. So that's a neutral. And similarly, in the donor region, you have donors and electrons. Okay, so yeah, quasi-neutral regions. All right. So what happens if you have a quasi-neutral region like this? What happens if you have a depletion region like this? So you have a region where you have a positive charge and you have a region where you have a negative charge. So there is going to be an electric field. Okay, because of because of space charge implies electric field. What is the direction of this electric field? This is very, very important to understand semiconductor devices. Whenever you look at any charges, look at what direction the fields are, right? So now the field is going to be in the direction opposing x. Like if I take x from left to right, the field is going to be from right to left, because On the right, we have the donor atoms, and those are positively charged, right? And on the left, you have acceptors which are negatively charged. So, yeah, right to left. So you have this charge. So what if you have a charge? Well, this charge helps in opposing the diffusion. Okay, so the field, E field, due to space charge, opposes diffusion. Okay, why? Because diffusion is because of driven by the concentration gradient. So there are excess of holes in the p side. So they'll try to get to the n side. But once this depletion region is formed, the electric field opposes further flow of holes. Similarly, it also opposes the flow of electrons from the n side to the p side. All right. So because of that, there is an equilibrium reached. Okay. So the forward driving force is the diffusion. The opposing force is the depletion field or depletion region that is formed, and that is creating an electric field. So because of that, there is an equilibrium, and that results in what is known as a built-in potential. Okay. Equilibrium achieved. All right. So basically, this has a lot of implications. The size of the depletion region is going to have a lot of implications on our device function. So what I'll do is I'll try to plot to get an idea what is happening. Let's try to plot first the charge densities. Okay, so I'll call x equal to 0 as my metallurgical junction. I'll use xn as the edge of the depletion region on the n side, and I will use minus xp as the edge of the depletion region on the p side. Okay. So now let me try to do this. I'll take it like this. Okay, just for my convenience. Yeah. So now let us plot what happens with the free charges. Okay, I want to plot n or p, whatever. Okay. So how is the charge distribution of n? The electrons are negative charge. Let's plot it here. So the charge distribution is going to be like this, right? N, negative charge, and they're extending from xn to infinity. So this is how the charge distribution looks like. And what about p? P is positive charged, so edge of the xp. Okay. So remember, these are, I'm drawing like a rectangle, or it looks close to a rectangle, not exactly a rectangle, but in the real case, of course, this is going to be some sort of a smooth curve. But we will take the approximation. We will make an approximation that the edges of the depletion region are sharp. Okay. So yeah, this is your free charges, right? And these are holes, and these are electrons. Remember, no charges here, right? No free charges. Okay, hence depletion region, right? The definition of depletion region is it doesn't have any free charge. Okay, fine. So this is one part of it. Now I also want to plot how does the space charge look like, because that has a lot of implications for us. To do that, I'll take axis, and then I'll say I want to plot x versus rho. I'll just give a common name, rho. Essentially the charge density, space charge density. How would it look like? Take a moment and think about it. So this is going to be your, let's say, xn, and this is going to be minus xp. And 0 is the junction. So I'll say that I will have acceptor ions in the p side. So I'll make it like this. And I'm going to have donor ions on the n side. So this is going to be my positive charge. This is going to be my negative charge. Okay. So always remember, so this is an approximation. This is like, we call it a depletion approximation, which is essentially meaning that it's going to be abrupt. But if you do the exact calculation, it might turn out to be something like this. Close enough, okay? Actually, towards the end of this week, I'll show you a small tutorial where we'll actually show you how the calculation looks like with the exact simulations and then this approximation, depletion approximation. All right, so we have these regions. So what? So we said that, okay, there is going to be an electric field in this direction. All right. But then this will help us to calculate, right? We should be able to calculate the electric fields. Once we know electric field, we can calculate currents and all that. We can also calculate the potential, right? So we'd like to calculate the current. So we have a situation where, I'll just repeat it for our completeness. So there's a positive charge and a negative charge, okay? So this is, let's say, rho. What is the magnitude of the charge? This we already defined as xn. This is minus xp. What is the magnitude of the positive charge? Think about it carefully. So if you are thinking about a diffusion process, right? Because holes are diffusing and electrons are diffusing from the n side to p side. So when they diffuse, you might be tempted to think that there is going to be some sort of a gradual variation. But always remember, when the electrons leave, the positive charge is coming because of the fixed charges, and those are uniformly distributed because the doping is uniform, right? So because of that, your profile here, this is constant because uniform donor doping, right? So it is a constant. So what is the charge? This is going to be Q times ND. So basically charge of electron times the donor atoms. And then similarly on the acceptor side, it's going to be minus Q times Na. Na is a density, charge Q minus because it's a negative charge. All right. Okay. So now how do we solve this? To solve this, we need to solve Poisson equation. You might have been familiar with Poisson equation. Essentially, it tells you that the Laplacian of voltage, potential V, is going to be equal to minus rho by epsilon naught. Rho is your charge density. Okay? And we can rewrite this. Sometimes we also call it Gauss law, which essentially tells you that dE by dx is going to be rho by epsilon. Okay. And this epsilon is the permittivity of the material where we are solving it. Okay. So in this case, we will solve it in silicon. So we'll say silicon. So this is permittivity of silicon of Si. If you solve it in gallium arsenide, that's going to change slightly. All right. So we have Gauss law. How do we solve it? Well, to solve this, we can try. We have to do it in two regions because we have uniform doping in x greater than 0 and x less than 0. So let's take the case x is basically between 0 and xn. What should happen? Since dE by dx is rho, so dE by dx is equal to rho by epsilon naught. So rho is Q and D by epsilon silicon. Right? This is the equation. So this implies that electric field is going to be Q and D by epsilon silicon times x plus constant. I mean, that makes sense. We have a constant doping, so it's going to be linear. Okay. Before we solve it further, let's try to think about what direction the field should be. Okay. What should be the qualitative behavior of the field? Okay. So can I have a field which is looking, it's going to be linear, right? So is it possible to have a field which looks like this? E versus x. Can it be this? This is a linear function, right? Would it work? Well, if you have something like this, it's not going to work. The reason is, remember, this is, let's say, xn and this is xp. Outside the regions, outside the depletion region, right? We said it is quasi-neutral regions having a lot of free charges. Whenever you have free charge, if there is, let's say by chance, some electric field, small electric field, they're going to rearrange in such a way that the electric field becomes neutralized. Okay. So because of that, in the quasi-neutral regions, you cannot have no electric field in the no E field in quasi-neutral regions. All right. So this sort of function cannot work. Similarly, this function also will not work. Right. Same arguments. So you're reduced to, just a moment. Yeah. You're reduced to finding a function which has to be zero on the outside regions. Only in the depletion region it has to be non-zero. Right. So is it possible to have uh, something which is like this? Okay. Well, it turns out that whenever you have sort of a jump like this, right? So this is, let's say this is minus xp and this is xn. If you have a jump in electric field like this, it has to be, it has to have a charge at the interface, okay? Which is not the case in this. So this also will not work because you might have studied in electromagnetics that whenever you have a jump in the electric field, there is there's a charge density associated with the interface. Okay, that won't work. Fine. So what is left with us is basically which is looking something, okay. Let me do it this way. Yeah. So what will be left with is something like this. This is one possibility, and this is another possibility. Okay. This will satisfy our equations. Okay. So this or this. So fields are zero outside, and it's continuous at x equal to 0. Okay. But out of which only one is correct, other one is wrong. Xn, this is minus xp. And the correct answer is the bottom one. I'm telling you the answer. We will show you mathematically. You can always get lost in the mathematics, okay? But physics cannot be wrong, right? Physics, finally, mathematics has to agree with the physical or qualitative picture, qualitative understanding. So the reason we say electric field is negative, E field, E is negative, because we saw, right, in the space charge, we said that the field is pointing in the minus x direction, right? So if the field is pointing in the minus x direction, as x is x is increasing, it should be in the negative direction. Okay. So because the field is in the opposite to the x, that's why it has to be negative. Okay. So yeah, let's try to do it mathematically. Okay. So let's just make sure that you have this in mind. Okay. So let's take the equations and solve it. Okay. We'll get to the answer that we just discussed. So let's say your for x is in the range in the n region, dE by dx is basically q and d by epsilon silicon, right? This is your Gauss law, right? And so E is going to be q and d by epsilon silicon into x plus c, right? So remember what we said. At the edge of the depletion region, the electric field has to go to 0 because beyond that it is just 0. I mean, it's not a pure metal, but it's it has a lot of free charges, right? So E equal to 0 at x equal to xn. Okay, because outside field has to be continuous. Remember, in the quasi-neutral regions, field has to be 0. Well, we'll correct it, okay, but later on. But right now, field is 0. Okay, so what happens? So C is going to be what? So minus q and d by epsilon silicon into xn, right? So your field is going to be E is equal to I like to make it minus QND by epsilon silicon into Xn minus X. Okay. So this is the field equation for the field. And then what happens on the P side? Well, something similar happens on the P side. Let's say I'll consider between minus XP and 0. dE by dx now is going to be what? It's going to be rho by epsilon. And rho, remember, is uniform, right? So it is minus Q and A by epsilon silicon. Right? This is your charge density divided by epsilon. And so that implies that your field is going to be minus Q and A by epsilon silicon times X plus C. And now E is 0 at X equal to minus XP. Right? So what does C turn out to be? If I put X equal to minus XP, my C will turn out to be minus will go out, so on the other side, so basically it's going to be minus Q and A by epsilon silicon times XP. Okay, so the E field is going to be minus Q and A divided by epsilon silicon times X plus XP. Okay, so now is it making sense? Well, let's try to plot it. Okay, one of the ways to check that would be if you take an axis like this, and then I take my X. This is your X, and this is your E field. So the way this is plotted, right? This is a linear function, and it's negative. So this is going to be your E field. This is Xn, and on this side you have XP minus XP, sorry, and the E field is going to be like this, right? So this is how electric field looks like. Okay, and one of the checks would be it has to be continuous. Okay, whenever there is no additional charge at the interface, it has to be continuous. So E is equal to 0 at X equal to 0. Sorry, not 0. I'm sorry. E is continuous, right? X equal to 0. So let's say this is 1, and let's say this is 2. E has to be continuous, so I'll put X equal to 0. So this is going to imply minus Q and D divided by epsilon silicon times Xn is going to be minus Q and A divided by epsilon silicon times X. Sorry, this should be minus XP, right? This is XP, right? So this is, sorry, I wrote first the N side, so this is correct. And for the P side, X equal to minus XP, this is correct. Please make sure that you work out these things. I mean, these are not complicated math. It's simple, fairly simple algebra, but you should work it out so that you're convinced. Okay. So now these things will go out. So negative charge also goes out. So essentially we are getting a relation which is telling us that ND times Xn is going to be NA times XP. This is a fairly important relation for you to remember whenever you are analyzing PN junctions. What this is telling you is that, remember, ND is the doping density, right? And ND is a donor density times the depletion width on the N side is going to be equal to Na times the depletion width on the P side. So if you think about it, this is essentially saying that charge is balanced across the junction. You can't have different amounts of charge on N side and P side. Okay. You can have scenarios where you have, let's say, I can have, Okay, we will come back to it, okay, in a moment. Basically, I can have a large ND. If I have a large ND, my Xn is going to be small, right? And Na can be small, so Xp is going to be large. Eventually, the product of ND Xn should be equal to Na into Xp. This is the criteria, okay? So this cannot be violated. The total amount of charge, like in this picture, what we are showing, right? Here, this picture, the area of the rectangle on both sides has to be equal. Okay, there's no other way because other regions are quasi-neutral, right? They are not contributing to any charge. So the charged region should be in such a way that there is positive and negative, and the total amount of positive charge should be equal to the total amount of negative charge, right? So this XP is telling you the depletion width on the P side. So 0 to XP is the depletion width on the P side multiplied by the magnitude of the charge Na should give you the area of this rectangle, right? Similarly, Xn times Nd. So this one should give the area of the rectangle on the positive side. So the total charge should be equal to this. It has to be balanced. Okay, that's all this is telling you. So do remember this equation. We will use it repeatedly. Okay. All right. So we are able to get to the electric field. What then? Okay. So once you have an electric field, we can compute what is known as the built-in potential of a semiconductor. So that can be done fairly simply by considering, let's redraw the electric field for reference. So I'm just doing it multiple times because I want you to be comfortable drawing these diagrams. So these might look like sketches, but then they have a lot of insight that you'll really benefit from. Okay. So this is your X and this is your electric field. So this is going to be my Xn and this is minus Xp. All right. So what is my peak electric field? Remember, what is my peak electric field? On this side, the equation was, let's try to guess it. The equation was minus Q and D divided by epsilon silicon, and at x equal to xn it is 0, right? So I have x is going to be positive here, so it should be xn minus x. As x increases, the electric field decreases, so it should be this, okay? Xn minus x. So if you try to memorize these equations, it will be difficult. So I would advise you to simply think about it this way, okay? What will be the electric field on this side? Electric field is going to be same, minus QNA divided by epsilon silicon times, now at x equal to minus xp, it's going to be 0. So it has to be x plus xp, so that whenever I put x equal to minus xp, it will go to 0. Okay, so these are the equations. So what is the peak electric field? Let's call this as E0, okay? E at 0, right? Is a peak electric field. How much is that? I mean, it should be on either equations you can take. E0 equal to minus Q and A by epsilon silicon at x equal to 0. So it should be xp, or rather, yeah, xp. That should be equal to minus Q and D xn divided by epsilon silicon. Okay. So this is going to be equal, right? We saw that xp into Na equal to xn into Nd. So this is going to be equal. All right. So this is your electric field. And from here, we can calculate what is known as built-in potential. Okay. Because whenever you have an electric field, right, if you integrate it, essentially you get the potential. Okay. So we know that electric field is going to be minus dV by dx, right? So V is simply going to be minus integral of E dx. So I just need to integrate this. Okay. So I mean, there are two ways, a hard way and an easy way to do it. The hard way would be to try to integrate it carefully and then solve for it. Okay. You can do it, but I'll leave it to you as a homework or exercise. What I'll do is I'll take an easy approach. I'll say that this integral is simply area under the curve, area under the E field, line basically. Okay, so the potential is simply going to be this area. That's the meaning of integration anyway, right? So what is this going to be? I'll say V built in is going to be E naught, okay, which is okay, no, half, right? Half width into height. The width is xn plus xp into height is going to be E naught. E naught is going to be, let's take one of the expressions, let's take it to be minus Q and A. Well, minus is not required because we're calculating area. It's not going to be minus Q and A divided by epsilon silicon into XP. Okay. If you try to rearrange it, I can write it slightly differently. I can take Q out and I'll also take epsilon here, 2 epsilon. And then I'll say NAXP equal to NDXN. So basically it will be ND times XN square plus NAXP into XP. So that's going to be NAXP square. Okay, this is an expression for built-in potential of a device. Okay, even though this is algebraically, it seems interesting, we almost will never use this expression. It only is telling you, the relevance of this expression is only to tell you that the potential is quadratic. Okay, it's a square. It's not a linear function, but it's a square. So the way the potential is going to vary across a junction is going to be this way. So you have minus xp, xn. Of course, we have to take a reference. So we'll take at x equal to xp, minus xp as 0. And then you'll see that the potential is going to change in a quadratic fashion like this. Outside these regions, electric field is 0, so there's nothing to integrate, right? So this quantity we call as V built in. Okay. So right now what I said was, okay, we argued it from the mathematical standpoint and said that there is going to be a if there is an electric field, there's going to be a potential, which is simply integral of the electric field. So in the next lecture, we'll talk about the physical, how can we intuitively understand it based on the band diagrams and so on. So next lecture, we'll deal with that. But right now, I just want you to understand the basic electrostatics. Okay, what we have done is not very complex. You should be able to draw the space charge region, how if you have an abrupt junction, and then how the electric field looks like. And then you can also analyze how the potential is going to look like. Okay, so please verify, this expression that I have drawn here, this is going to be the answer that you get if you try to integrate it. Okay, if you try to integrate the electric field, you'll get this. Okay, please verify that you get that. Okay, and that will be a good homework for you. I'll see you in the next lecture. Thank you so much.